Hi folks, today we will learn a very important concept and it is Bernoulli's theorem. So, but not Bernoulli's theorem exactly, but Bernoulli's equation. That's what we will see it here. Okay, so Bernoulli's equation. So we have this Bernoulli's equation. We will derive it actually. So in Bernoulli's equation, we are actually going to find like how if there is like this pipe this pipe I draw it. Okay, I'm drawing a pipe here. I'm drawing a pipe here. Ignore my drawing skills. Please focus on the concept here. Okay, so this is a pipe in which there will be water flowing. So earlier you might have studied this, that if like there is a beaker in which there is water, say there is water. So pressure pressure inside this liquid is rho gh, where h is, you know what, depth depth of liquid depth of liquid from sorry depth from the sorry it's depth from the liquid of from the surface of liquid. I'm really sorry, actually I was just seeing somewhere else. I was seeing if my camera is working properly. So it's like depth of depth from the surface of liquid. Hopefully this R is visible in camera. Actually I have very poor camera for now. And so if like assume this on an average, this portion of pipe is like this is h one height above from the ground, h1 height above from the ground. And this portion here, this is like assume on an average its height it is h2 from the ground. And then like there's water flowing in this, like say we had like water molecules here. So water molecules are continuously flowing in this pipe, you know, from here till there, like water flowing. So water flows from here, like suppose we come across a water layer here. Here is a water layer. It traveled from here, it entered and it came to this is the layer of water. Okay, say this entered like this entered with speed v1 from this entry gate, and then this will exit from here. Say this took exit from here. Then I'm just trying to draw the, when it will exit it will create a cylindrical shape of liquid. The volume of liquid will create a cylindrical shape, you know. It will like it will suppose it will have velocity v2 while exiting. And why we are saying that if this velocity is v1 then this is v2, why not v1, like why not velocity remains constant? It's because you see the cross sectional area here. This is cross sectional area a1. This like it is quite different from this cross sectional area. This is suppose a2. So if a1 is different from a2, which are cross sectional areas, and you might have stated this, that a1 v1 is equal to a2 v2. That is the product of area, cross sectional area, and velocity of the fluid is constant, which means if area increases velocity has to decrease, and velocity increases then area has to decrease. So you know, like if if the product of cross sectional area and velocity has to be constant, that implies that if area changes then velocity also changes, you know. That's how it works. And then we have like and this how you think these water molecules traveled ahead? Because you know, if this their water molecules which came from here to here, like the water molecules which are preceding to these water molecules, they are exerting force. That's how they are traveling. They exert force. So say this is actually a part of pipe we have taken. There is a whole long pipe out there from which we have taken a part. So there will be also here like water. There will be like water molecules here exerting force, say P1, say F1 force being exerted on preceding water molecules by what preceding water molecules. Then this, say this travel distance is d1, and then we again have like, I'm sorry, here we have like this take m from v2 speed. Say this layer traveled like v2 speed, sorry, I mean d2 distance. This is d2 distance, this was v2 velocity by which the water molecules were coming out of this pipe. Now we will, like we have system, and our system contains this pipe, not actually this pipe, the water molecules which are inside this pipe, and this ground, they are part of our system. And we will use conservation of energy, which is like energy initial plus work done by external forces on our system is equal to energy final. This is the formula of conservation of energy. So we will find this term by doing some calculations, and this term, also this term. Then we will plug in all those terms in this equation, and then we will have our beautiful Bernoulli equation. In the last, in the end of this video, I will also tell you a trick to learn that Bernoulli equation if you don't know. By the way, that trick is pretty famous already. So we will like, if we find energy initial. So initially what was it, like we had a pipe and in which there was water. So if you want to find the initial energy of the system, we will like find it dividing it by in two parts. First we will find the initial energy of the system, and then this system, this part, sorry, this part. And we don't have to actually find the energy of this part, because we will assume it to be E naught, because when we do calculations it is going to get cancelled out, so we don't have to worry a lot about this. Now we will focus on the energy of this. So what is it going to be, let us see. So it like it it has a velocity v1. The water molecules which entered through this, like they created a cylindrical shape, kind of cylindrical shape, did they? You can see it clearly, cylindrical shape. So they were entering with velocity v. So let's write energy initial, and there are also some h1 height above the ground, so they will have gravitational potential energy as well. So their gravitational potential energy is simply like, you know, the expression of gravitational potential energy, mgh plus half mv square, that is the like formula of kinetic energy. Now like, so we will write mass in terms of density and volume. We assume the density of this liquid is rho, and volume of the volume of the liquid which has been entered here is v, say v. And height, you can see it is h1 from the ground. And again we will write like rho v. Okay, did anything go wrong? So here I forgot to write this term, this thing. So let's do that. So we are writing mass in terms of like density and volume, density of liquid and volume of the volume of the liquid that has been entered. And this is again we have gravitational acceleration due to gravity. Then we have to put the value of height, which is h1. Okay, then we have like half, again we will write mass in terms of density and volume. Density of liquid is say rho, and volume we already assumed it to be v. And the velocity which by which it entered is v1, you know that. And this like E1, E, E initial, it's like E initial. E initial we are getting is rho Vg H1 plus half of rho V and V1 square. Don't get confused. This is volume and this is velocity. And also we have like calculated the energy of this part only. Now the energy of this part we assume to be E naught. So we will also add that. Then we get energy initial. Now what about this? What about like work done by external forces on our system? This is work done by external forces on our system. So we'll find that too. So work done by external forces on our system, that has to be calculated. Okay. Now let's focus on that. So work done, it will actually, so these water molecules are applying F1 force, and then like this what as water molecules go ahead, the water molecules which are ahead of even them, they apply F2 force and opposite to the flow, you know, direction of flow of liquid. So we'll write that. So work done by F1, let us see what is that. So work done by F1 is like F1 into the displacement which we assumed D1. So we put here that. Now this force, since force and displacement are in opposite direction, they are opposite to each other, so we'll have a negative sign before that. Then we write F2 D2. Then we have like this. And what is force? Force is nothing but pressure into area. Like we can write it in terms of pressure into area, because pressure is force per unit area. So force is like pressure into area. So we write P, say here the pressure was developed due to this force and area. So it was P1, let us say, and here it was P2. So we say like P1 A1 and D1 minus F2. Sorry. Here we have P2 A2 and D2. Similarly, now what is this? Desert. This is something you might just like okay, this is like area into distance. Like this is the cross-sectional area of this cylindrical shape volume of liquid, and this is height of the cylindrical shape. So it actually becomes volume. And what about this? Will it be same like it was V volume? Will it also have the same volume? Yes, because we are taking it as ideal liquid. Like ideal liquid means like incompressible, which which cannot be which cannot be compressed. So since it hasn't been any compressed, so it will have same volume. Yes, so we keep here V, and we like factor out V. So we get P1 minus P2 times V. Again, like we have found work done by external forces on our system successfully. And energy initial 2, we have this energy initial 2, and we have this all. Now the last thing we have left to find is energy final. So how do we do that? Okay, this is energy final. So what was the final state of our system? In our system, and finally we use water layer. This traveled like this came here, and which had entered, and this also took an exit later on, like here. So this was our final system, and we already assumed the energy of this part. This part you can see from this part, E naught. So energy of this part will be E naught, and we want to find energy of this part. We'll again have to write like gravitational potential energy of this part, which will be like mg h mg mass into acceleration due to gravity and height. Okay, and we'll also have, in addition to this, we'll have like what is it, yeah, kinetic energy. So we'll write E naught as it is, and mass we'll again write in terms of like volume. And I have told you the volume of this liquid is same as that of this liquid, because it is incompressible. I mentioned it earlier. So that's like, and we'll write in terms of density of liquid and volume. density of liquid and volume. Okay, rho vgh. Okay, then we have like half again mass, but here we will have v2 because you know here it was v2 speed. This was coming out by v2 speed. So we have this all. We have all. We have successfully found all three terms of our objective equation. This was our objective equation in which we had to find energy initial, work done by external forces on our system, and energy final. We'll plug into all these values of all these three and we will get the equation. So let us do that. So by doing so we will get like, let me check. So what energy initial, what was, okay, I remember those terms. Let's write them here. What was like, we had energy initial which was like rho what was rho v, okay, and what was it, rho v mg is right. So we write and this is g, again this is h1, then this was like half rho v and v1 is square. That's energy initial, then we are like work done by external forces on our system, and this was, we like, we took out v common, then we had p1 minus p2, we had that. And on the right hand side we had energy final, which was, which we found later earlier, like we found like rho into volume, like, and g h2 plus what was like plus, what was it, and again I forgot something. In energy issue there was e naught 2, you know. This is like worked upon by external forces on our system. This is energy initial and we are writing here energy final. So we are like, this was the expression of gravitational potential energy, then we had like, what it was, okay, here we had kinetic energy half v rho and v2 square, then we had e naught here, now see here e naught get cancelled from both the sides, then you see this volume term is in each expression, so we factor out it and cancel out from both the sides. You see, then we get like, here we have p1 minus p2, right? So you see like 1 1 1 2. So why we keep to this here, let's send it on the other side on RHS. So we'll get rho g h1, plus half rho p1 square plus p1 is equal to p2 plus rho g h2 plus half rho v2 square. Okay, now we'll just rearrange it. P1 plus rho g h1 plus half of rho v1 square is equal to p2 plus rho g h2 plus half of rho v2 squared. This all we have. So to learn it, the trick is simple. Like you already memorized. I hope I expect that you already memorized. Like the expression of computational potential energy and kinetic energy, like they are taught in very early classes. So I am expecting that you know that already. So what we have to do, just replace mass by the density of liquid, that is rho, and by doing that replace like replace mass term by density of liquid and sum of them, add them both, and then add pressure also, like we will get the equation pressure, and there is an expression like there is this term that is similar to like the expression of, we have like gravitational potential energy, and then we have like potential energy expression, and then this term is very similar to very similar to what very similar to kinetic energy. And this term also, like, you can write it like this: v1 plus rho h1 plus half rho v1 square equals to constant. Again, just to make it simpler. Okay, that was it for today. Like, guys, and hopefully, I don't think. Okay, okay, guys, okay, guys. Hopefully, you enjoyed it. I assume that you enjoyed it. Even though the video wasn't that good, I'll try to improve in further upcoming videos. So guys, that's it. See you. Bye.